Okay, so we have started recording and I will start the backup also. Okay, we are set now. Fine. So I believe you must have seen the schedule which I have uploaded in our course website. So this is our schedule. So as you can see, we are planning to release our assignment 2 this Friday on October 8th, and the deadline is sufficiently relaxed. It is October 21st after the Durga Puja holidays are over. Next week is practically a holiday except for Monday, where we are going to have a class. We do not have a holiday on Monday. The deadline for this submission will be the week just after the Durga Puja holidays are over. The usual time 11:55 p.m. Please note this is not 11:59 p.m. And in the week number 12, that is this October 25th to 29th, on the Wednesday of that, we are going to have our second online test. And in that second online test, the syllabus will be from like whatever we started after our assignment 1, meaning the shear stress in beams up to this miscellaneous applications chapter that we are going to start today. Okay, so starting from, so if you just look here in our course home, you have these different chapters. In the previous week, we had completed this thing, the transformation of stress and strain, this one. And this week we are going to start with miscellaneous applications. So depending on how much, I mean, we have holidays and such other things. So this 1 or 2 weeks I have kept a little bit flexible. So we'll try to see how much we can cover. Okay, but our syllabus will be from here to here. So shear stress in beams and thin wall members starting from this chapter. This one, transformation of stress and strain and miscellaneous applications. Okay, so there is a common thematic commonality among these 3 chapters. So it's a good thing to have it in one test. And the third test, although I have not put it in the schedule, let me just tell you, we are planning to have it at the very end, means something like November 20th. Okay, so I'll put up a notice for that also. In all likelihood, it will be extremely convenient for both Professor Archana Arvind and myself if we can have it on November 2020. Okay, so just a heads up regarding that. Now, we are going to start with this miscellaneous applications chapter. Now, in the previous chapters, we have been learning various things. Especially in the previous chapter, we have learned quite a few fundamentals of the theory that has to do with stress, transformation of stress, strain, and transformation of strain. And especially when we were doing the transformation of strain, we brought in together many things at the same time. So first of all, when we were doing the tutorial sheet number 4 on the transformation of stress, we were dealing only with the stress part. But when we did the tutorial sheet number 5, I gave the questions in such a way that it covered not only the transformation of strain, but also the transformation of stress, and the connection was through the generalized Hooke's law. So that is a step towards how in actual applications everything comes together. In addition to these transformation of stresses and strains, you have also studied various ways in which stresses may arise in shafts and beams, starting with torsion, then going through the bending of beams, where you talked about the bending moment and shear force diagram, and then we talked about the shear stresses in beams also. So in this particular chapter, through various kinds of practical applications, we are going to see how these various application concepts as well as the fundamental concepts will be brought together in the solution and design of certain situations, in the solution of problems and the design of certain situations which are of extremely great engineering importance. Okay, and the first topic that we are going to cover is something which is widely used in almost all factories in different kinds of industries. Okay, so this is the topic of thin walled pressure vessels. So let me go to that, to the writing app, thin walled pressure vessels. Now in the spring semester of basic engineering mechanics, this topic was covered, at least the theory part of it was covered more or less completely, but there were certain things which were lacking, in the sense that even though we covered thin walled pressure vessels, but in the tutorial sheet we only gave 3 very simple problems. Okay, so there was a tutorial sheet number 6, and please note that the autumn semester guys and the spring semester guys of basic engineering mechanics, the tutorial sheet numbers got completely changed. We revised the tutorial sheet number. We wanted to organize it in a certain different way. So when you talk with each other, perhaps please note that the numbers were completely different. There was a certain tutorial sheet in which there were only 3 problems from these thin walled pressure vessels. And our limitation was that back then we had not covered the transformation of stress and the transformation of strain properly. We discussed something in a very brief detail, and in one of the immediate assignments, some questions were also set, but that was in a very incomplete, haphazard fashion. Okay, now that we have completely devoted 2 solid weeks on transformation of stress and strain, we can address the real like proper problems in thin wall pressure vessels nicely. But as I said, since the autumn semester guys have not done even the theory part of this thin wall pressure vessels, I will go through this in proper detail. So in many engineering applications, in many engineering industries, these kinds of thin walled pressure vessels are used. Now, what are these thin walled pressure vessels? Well, it's best to discuss this by giving 2 of the things which we are going to discuss in detail, and that is a cylindrical pressure vessel. So it is something like this. So this is just a very theoretical kind of drawing. In practice, what you will have is that this is like a very, very big cylinder. It may so happen that this cylinder has a diameter. So this diameter is of the order of 1 meters or even 2 meters. So I mentioned this to the section 20 students of spring semester BM, that you understand, you get a feel of what I'm talking about here. 2 meters diameter. Okay, just pause for a second and think about it. I mean, the height of an average Indian, male or female, it is not more than 2 meters, the height. Okay, and here you are seeing the diameter of this is that. We are not even talking about the length of this cylindrical pressure vessel. Length is even larger. So these are huge structures. Okay, and these kinds of pressure vessels, what they contain is that there is some kind of pressurized fluid inside it. And you all know by now that fluid can be either a liquid or a gas. So very high pressure fluid is maintained inside this thing. Okay, very tightly sealed. And because of the huge structure of this thing, they are usually placed not inside the building of the factories or industries, rather outside the buildings. Okay, like a dedicated space is present where these pressure vessels are present. Some of your parents may be actually engineers, and you can talk to them, like their main job will be to deal with the maintenance of these pressure vessels, extremely critical components in the smooth running of a factory. You can talk with them, get a feel. And if you have some special ideas, some modern or innovative practices which are currently being utilized, I welcome you wholeheartedly to share those things with us. Okay, if your parents are those kinds of engineers, please do share with those kinds of things. However, I'll be dealing with the fundamental things. Please also note that it is not just extremely high pressure. Sometimes these liquids or gases, they are present at very high temperatures also. So it is extremely important that these pressure vessels are designed in such a way that there is absolutely no possibility of these things bursting open. Okay, because there is a real danger that under this high pressure and temperature, these things can crack, burst, and due to the ensuing explosion, there can be a very bad accident. And please don't think that this is just like a theoretical possibility. Such kinds of accidents have actually happened in history. People's lives have been lost, like so much money has been wasted on these things, both loss of life and property. Okay, so these are extremely important components. Please also understand that when these are installed outside the buildings, they are given some kind of supports. Okay, they are not just floating in space like this, but for the purpose of clearly understanding this structure and this thing, I have not drawing all those supports. Another very common kind of pressure vessel is shaped in the form of a sphere. Just a sphere. Okay, of course, this sphere is just not placed on the ground like this. There are some supports like this, okay, or some other kinds of supports. I'll remove these things. Okay, and there are many design considerations associated with those also. But what we are going to focus on within the context of mechanics of solids is that how or what should be the dimensions of these pressure vessels, meaning that one important thing to remember here is that this thin walled nature. Okay, so I'm just drawing a little portion of this thing. This wall is very thin compared to the overall diameter. So if the overall diameter is, let's say, 1 meter, this thickness here will be something like 15 millimeters or 10 millimeters, something like that. Okay, so 1 centimeter compared to 1 meter. So just understand the difference in the magnitude. Similarly here. Okay, and the stresses which are developed in these pressure vessels will be critically dependent on the thickness. Okay, and we'll see how this is coming about. Now, in order to understand how the stresses are being generated, so before you even go to the formula, can anyone tell me that why do you think the stresses are generated in these solid parts? Why do you think such a thing is happening?
Because of the pressure in the fluids contained in the vessel.
Please say that again, I could not hear you.
So, like because of the pressure that exerts because of the fluid inside.
Yes. So yes, so because of the pressure which is present inside it, you can almost think of it, you can draw an analogy, even though it is going to be a very bad analogy, but for the purpose of imagining and understanding the thing, it's a good analogy, I think, that you can compare this with a balloon. Okay, like the balloons children play with, that balloon. When you are blowing into the balloon, initially you know that it's quite safe, it is not going to burst. But when it has reached a certain large size, the balloon, when you are blowing into it, and you keep on pushing air into it by blowing into it, you know that it is coming to a very critical stage. If you still keep on blowing into it by increasing the pressure inside, you will reach a stage where the balloon will just burst. And that bursting happens because the membrane of the balloon, that rubber membrane, that tears open. Okay, and just like you have that kind of a rupture or a tear in the membrane of the balloon, that happens because of the stresses generated in the membrane. So also it may seem quite funny to compare this kind of a structure which is made of a solid steel material, but you understand that the overall magnitude of everything, the pressure is huge here. The thickness is very small. So it is almost like a balloon. okay, which is under extremely high pressure and temperature, and there is a distinct possibility that the stresses will be generated to such an extent that it can burst open. Now, what do we do in order to actually get an estimate of this kind of the stresses which are generated in these cylindrical and spherical pressure vessels? Think about it for a moment. The theory behind it is quite straightforward actually. Okay, it takes barely 5 to 10 minutes to derive that theory. Although I have made a 1 hour video by talking very slowly about it, and I've shared the video link with you, the YouTube video. That's almost a 1 hour video lecture, but it can be condensed to 5 to 10 minutes, the actual derivation. So I want you to think about it a little bit. What can we do to arrive at the stresses? People who have already gone through the video lectures, you know the answer, then don't answer maybe. But if you have any confusion, please, you can make a comment about it or something. Okay, I will ask you a few questions. You try to answer, and then that discussion will motivate us to arrive at the way in which these derivations are done for the stresses. First of all, you take your mind back to the transformation of stress chapter, or just generally the stress. What kind of transformation of stress we have done? We have done both two-dimensional stress transformation as well as three-dimensional stress transformation. When we were doing two-dimensional stress transformation, what kind of condition did we use? My question to you is, what kind of condition did we use to arrive at those formulas in the two-dimensional stress transformation?
So sigma z is 0.
Sigma z is not just sigma z is 0. We also said that yes, sigma z is equal to 0, tau zx equal to 0, tau yz equal to 0. So that is with reference to a particular way in which the coordinate system is set up. In general, the condition that we were discussing for the two-dimensional stress transformation was the condition of plane stress, where the entire business was taking place within a certain plane. And for the purpose of our discussions, we had taken that plane to be the XY plane. Now you think whether it may be possible to borrow the ideas from that two-dimensional stress transformation to this thin-walled pressure vessels. If I were in your place and if my professor had asked me this question, that if it is possible to borrow that idea directly to this thin-walled pressure vessels, my answer would have been a no. Why it is no? Tell me.
Sir, there is sigma z, that is the pressure from the fluid inside.
Yes. Any other reason? Any other reason behind besides the pressure? See, my question to you is that is it perhaps possible to borrow the ideas of plane stress? So plane stress means we have a little element like this. Its thickness is very small. This is perhaps lying in the XY plane like this. XY plane like this. And there is no pressure in the Z direction. There is no stress in the Z direction. Everything is happening within this XY plane. So from this, I want to borrow these ideas to this thing or this thing. One reason why your answer could be a no, that you cannot borrow these ideas here, is that one of the conditions which is necessary for plane stress to be valid is that you should not have any pressure like this in the Z direction. This should not be present. But here, if we say, suppose that we take a little element like this, that we take a little element here, and I zoom into it, something like that.
Sir, one doubt, sir. Hello, sir.
Yes.
So do we consider the Poisson's ratio?
Do we consider the what?
Poisson's ratio.
Poisson's ratio. What about the Poisson's ratio?
So like if we do not consider that, then the sigma z will be 0, I guess.
Right. So we are going to consider the presence of the Poisson's ratio. Okay. We are going to respect the effect from the Poisson's ratio. Okay. Because this is a real world application. We cannot arbitrarily deny its existence. Okay. So we have to respect the effect of that. So you understand here that this almost looks like this situation, almost. But the first thing, which is a little bit of an irritation, is that this is not really a plane. This is slightly curved. Okay, this is slightly curved. You understand this, okay? Because this surface is curved like this. This surface is also curved like this. So whether you take a little element out of this here or a little element out of this thing, both of them will look like this. And this is a little bit curved. So from that perspective, it is definitely not a plane stress. Okay, because that word is embedded, plane stress. This is certainly not a plane. Now, the way that we come out of that problem is by saying that this diameter is so very large that if we take a small enough element, this curvature is very, very small. Because the diameter is so very large, the radius of curvature is very large. So this curvature of this element is very, very small. So for all essential arguments, practical purposes, we may somehow consider this curvature to be almost non-existent, and this is almost like a small, like a plane. That is one resolution to the problem. The other resolution is that even though there is a pressure in this direction, okay, in a direction which is normal to this element, but it will actually turn out to be so that the stresses which are generated in this direction and the stresses which are generated in this direction, these stresses are significantly higher than the stresses which are generated in this normal direction. I repeat, the stresses which are generated in this plane of this little element, they are going to be significantly higher than the stresses or the pressure which is present in this normal direction. So it is under these kinds of restrictive simplifying assumptions that we have to proceed towards our derivation. All right. So in reality, this is strictly not a case of plane stress, but it is only under this kind of simplifying assumptions that we can say that it is almost like a plane stress. And this is why it is extremely important not just to think purely mathematically about real engineering situations. Okay, so the purpose of our miscellaneous applications chapter is not just to give you a dictionary of new applications where you can just plug in the formulas and get your answer. In addition, that is certainly one of the motivations that we expose you to different applications. But at the same time, our motivation here is to also expose you to the thought processes which are required in order to carry over our fundamental theory to this new kind of applications with reasonable simplifying assumptions. Because only when you understand and respect those simplifying assumptions in a real practical scenario will you be able to understand, judge for yourself whether a certain formula is really applicable or not. This is the real take-home message here. Not just that you get a formula for sigma 1 and sigma 2 and keep on applying those things by repeatedly using a calculator or some Python code. That is not the real objective here. Okay. So please remember this thing. Okay, now that I have finished this lecturing business, let me get down to the actual derivation. So how do we go about this derivation? Well, as I have drawn it here, I have actually almost started the derivation. We are going to neglect this thing and we are going to talk about these stresses in this direction. Okay. Now, question may arise that why this particular orientation? Okay, I have taken an orientation of the stress element like this, but what is stopping me from taking an orientation of the element like this. I may very well make a cut like this, like an imaginary cut like this, take out an element like this. Okay. Consider this thing. What's so wrong with that? Does anyone have the answer for this? If we do like this, what is going to be wrong about it?
So we need to find two more variables. I mean, the shear stresses.
Okay, so you are saying that if I consider an element like this, I will have stresses, these normal stresses. But in addition to that, I am also going to have these normal stresses. This is what you are saying, right?
Yes, sir.
Okay, which means that you are kind of implicitly telling me that when you are taking this kind of an element, there is no need to consider these kinds of shear stresses. That is what you are implicitly telling me.
Yes, sir.
Why are you telling me that? That in this case, these kinds of shear stresses that I have taken, you are implicitly telling me that this is equal to 0, this is equal to 0, correspondingly its brothers and sisters will be equal to 0. But in this case, this is not going to be 0. Tell me why. You are correct. This is going to be actually 0. But why?
Sir, that is one of my question. I mean, I got the same doubt while seeing the video, so I thought of asking that.
Okay, so anybody has any idea why? So I'm telling you, okay, this is a fact. This is a fact that if you take the element like this, where one of the sides, this edge, is parallel to the longitudinal axis of the cylindrical pressure vessel, and the other one is perpendicular to that longitudinal axis, you are going to end up with shear stresses which are 0. So you will only have the presence of these normal stresses. Question is why?
Sir, is it like experimentally, if we observe, there will be no the kind of shear when we observe in a practical situation?
Yeah, that is certainly true, but that is like a circular kind of logic. Okay.
Sir?
Yes.
Yeah, can we say that it's because of the symmetry of the system? Like,
What symmetry? Because symmetry is a very, very sexy word. Okay. Now you have to tell me specifically what kind of symmetry you are thinking about. Left-right symmetry, up-down symmetry, what kind of symmetry?
so like, suppose in this element,
Yes.
like we are taking, say on one side, we are taking the shear stress in one particular direction. But if we inspect the element just beside that, then on the other edge, like it will be in the opposite direction, but there should be a spatial symmetry in this case because the two elements should be indistinguishable, technically speaking.
But that's not a problem, no, because if you take a little, let me delete this thing, okay. If you take a little element like this here, okay, if you take a little element which is just beside it, okay, I've just put this artificial gap in between this, but you understand that here also this will be like this, this will be like this, this will be like this, this will be like this. So you see there is going to be absolutely no difference between the way that the stresses are showing up here and the stresses that are showing up here. So they are practically indistinguishable. That is not the argument. Something else is going on here. I'll give you one clue. Look at the entire cylindrical pressure vessel and think of the way that the pressure is acting from it from the inside. In fact, I'll give you another clue. If you look at it from this end, okay, so let's say that we set up our x-axis like this. This is our y-axis and this is our z-axis. Okay, and you look at it in the YZ plane. So YZ plane, it will look like this. And the pressure is acting like this. What kind of symmetry is this situation?
Axis symmetry.
Yes, this is a situation of axis symmetry. Please remember this. Okay, so when you have a situation of axis symmetry, there is no variation. No variation in the theta direction. Theta direction means here we have used the XYZ coordinate system, but you may as well use this direction as R and this direction as theta. So in the theta direction, there is no variation. No matter which point along the periphery you sit, it always looks the same. Okay, so that is why we say there is no variation in the theta direction. And this means that no variation in the theta direction means that you are going to end up, okay, so basically this is this and the fact that there is no component of the internal loading which has a theta direction component. Okay, so it is purely in the radial direction, this pressure, because you understand that suppose I'm telling you, okay, this is very important to understand. Suppose our loading was like this. This is our pressure vessel in the YZ plane. And suppose our loading was something like this, that we are applying some kind of shearing stress on this internal periphery. Please tell me whether this is axisymmetry or not. Is this an axisymmetric loading or not?
No.
No, sir.
Wrong answer. This is still an axisymmetric loading. Axisymmetric loading does not mean there is no component in the theta direction. You see what I have written here? There is no variation in the theta direction. Okay, you can have very much a component of the loading in the theta direction, but there should not be any variation in the different points. Okay, so whether you sit here or here or here, they're all experiencing this kind of theta direction loading, but the magnitude of the theta direction loading is not changing as you go from different points. This is extremely important to you later on in your fluid mechanics also, when you are going to study various kinds of Couette flow. Okay, so exact solutions of Navier-Stokes equations, you're going to study Couette flow, you're going to experience this kind of things. Okay, and here also. So both in fluid mechanics and solid mechanics, this is a very common source of confusion among the students, that axisymmetry, it only and only means no variation in the theta direction. The fact that there may be a component in the theta direction does not prevent the existence of axisymmetry. However, the fact is that in this particular case of the pressure vessel, we only have the presence of this pressure, this internal pressure, and we know that the pressure always acts in the radial direction. And because of that fact, which is separate from the issue of axisymmetry, that we are not going to have any displacement in the theta direction. Okay, there is no deformation that is going to take place in the theta direction. So no variation in the theta direction means del theta of anything is going to be equal to 0. This is the implication of the no variation in the theta direction, and the implication that there is no loading in the theta direction means that, so this is a separate thing, that no loading in the theta direction implies that the V direction displacement, V means V is along the theta direction, okay? So V is equal to 0. Why I'm writing it like this, I'll tell you. You go back to the previous tutorial sheet number 5, and look at the last problem that I had given there. What is this thing? Epsilon RR. It is only dependent on this radial direction displacement, del U del R. This U is the radial direction displacement. Epsilon theta theta has both this U and R, but here you have this del V del theta. So according to the condition of axisymmetry, if you determine the epsilon theta theta, this term will vanish. It will become 0 because there is a del theta here. Axisymmetry means del theta of anything is equal to 0. Okay, so that is going to be equal to 0. You come to the epsilon R theta. Epsilon R theta has both U and V, but here you see there is a del U del theta. So del theta of anything must be 0, so this first term is 0. In the second term, you have the del R, but you have the del R of V. But you've already said that because pressure is only in the radial direction, the V must be equal to 0. The displacement in the theta direction must be equal to 0. So this V is 0. So this V is 0. So overall, this epsilon r theta is going to be equal to 0. Okay, let me come back to the writing up now. Because we have these things. Okay, so del theta of anything equal to 0 plus the fact that V equal to 0, these two things together imply that epsilon r theta is equal to 0. Now epsilon r theta equal to 0 means sigma r theta or tau r theta, because we are writing tau r theta, which is the shear stress, tau r theta is going to be equal to twice g epsilon r theta, that is going to be equal to 0. Okay, similarly, you can think of other components of this tau. This is just one of the components of the shear. You think of the other components of the shear also, whether they are going to be 0 or not. Okay, so please be very careful. Okay, it's very easy to just sweep things under the carpet and not to think deeply about it. But even under these small things, there are lots of things to think about. All right, so we proceed with the understanding that if we take an element like this, we are only going to have the shear stress. I again request you to please think about the other components of the shear stress also. Okay, so they are also going to turn out to be 0. So we only have these normal stresses. Now, because we have just these normal stresses, what do you think these normal stresses are denoting? They are on the planes. So they are on this plane, they are on this plane. What kind of planes are this then? Where there are only normal stresses?
Principal stress condition.
Yes. So these stresses, because they are on the kind of planes where there are no shear stresses, these are all principal stresses. These are all principal stresses, and these planes, so this plane, they are all principal planes. Okay. So if we had taken a cut like this in an oblique fashion, then we would have the presence of both the normal stress as well as the shear stress. Those planes would not have been the principal planes, and these normal stresses would not also have been the principal stresses. Okay, so now we have some in-depth understanding of this background. How do we actually determine the expression of these principal stresses? So what we'll do is we'll call this one as sigma 1 and this one as sigma 2 in the context of the cylindrical pressure vessel. And now the derivation is quite straightforward. So what we'll do is we'll take a cutting plane. Okay, we'll take a cutting plane parallel to the XY plane, and we are going to take, so let me draw this thing. Okay, we are going to take one cutting plane parallel to this XY plane and passing through the longitudinal axis. And we are going to take two cutting planes which are parallel to the YZ plane, like this. Okay, just to obtain the expression of this sigma 1. So if we do this, the kind of picture that we are going to obtain, it will be like this. Not the greatest of diagrams, sorry about that, but I hope you understand what I'm trying to draw here. Okay, so this is the thickness of the pressure vessel. You understand that this one here will be the sigma 1. This one here will be the sigma 1. On this thing where the liquid is present, okay, so this orange colored part So this orange colored part, this is where the liquid is, okay, or the fluid is. On that there will be some kind of pressure all throughout. So I'm going to write down the equation very quickly. So this distance, let's say this is delta x. This entire distance is delta x. This thickness is delta t. Of course, this thickness is t also. Okay. And the internal radius, okay, the internal radius of this pressure vessel is r. Fine. So what we are going to obtain is this thing. Check this out. So sigma 1 is acting over this thing. So this is T into delta x. T is the thickness and over this length delta x. Now this is just over this one, but it is also acting over this one. So there is a 2 factor involved. So I'm just doing the force balance in the z direction. Okay. What is this going to be equal to? Tell me. In terms of the pressure of the fluid.
Pressure into 2r into delta x.
E into twice r into
delta x.
Delta x. So for sigma 1, what I obtain is PR by T. That's it. This is one formula. Okay. And because you see that this is occurring, so if we look at it from the edge, okay, if we just look it from the in the XY plane, this is going to look like this. Okay, so this is referred to as the circumferential stress, circumferential or hoop stress. Fine. The sigma 2, what we'll do is we are going to just take a cutting plane parallel to the YZ plane, nothing else. Okay, not this, just one cutting plane parallel to the YZ plane. So if you do that, we will end up with a picture like this. And the sigma 2 that will appear in this fashion. Sorry. Like that. And the pressure in the fluid, that will be acting like this. Now you tell me what should be the force balance in the x direction. So let me write the one for sigma 2. Sigma 2 will be this area over here. I will write that in an approximate sense in this way, twice by r into t. Okay, because you understand that this thickness is t. The internal radius here is r. So approximately that area of that ring is twice by r into t. What is that going to be equal to in terms of the pressure? Tell me.
Pressure P into pi r square.
That's it. P into pi r square. So sigma 2 is going to be equal to PR by twice T. And this is another formula. And this is referred to as the longitudinal stress. And of course, you note that sigma 1 is equal to twice of sigma 2. So that's all there is to it for the cylindrical pressure vessel. Spherical pressure vessel is actually very easy, much easier than this cylindrical pressure vessel. So if we go back, axis symmetry, but there is even more symmetry in this spherical pressure vessel because it is a case of perfect spherical symmetry. Okay, so here you had the axis symmetry only about this x-axis, or if you want to consider in terms of an r, theta, z coordinate system, then the z would have been along this here. So the symmetry was around the z-axis. But here, no matter what axis you make, you consider, okay, so no matter what kind of axis you consider through this, through the center, like this, like this, like this, about any axis, there is perfect symmetry. Okay, so there is no distinction between any of these axes. Because of that situation, here we had the case of sigma 1 and sigma 2. Here it is going to be the same normal stress acting in all the directions. So it doesn't matter whether you take the little stress element like this or tilted like this or tilted like that. Any way you take, it's going to be the same kind of situation. So we just take for the spherical pressure vessel, let me just write this thing previously here. This was the cylindrical pressure vessel. For the spherical pressure vessel, you just take any element. The same stress is going to appear here, it's going to appear here, it's going to appear here, it's going to appear here. Okay, and even if you take an element like this, the same kind of situation is going to be like this. Okay, so these are all the same, sigma, 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 here also sigma, sigma, sigma. Okay, so doesn't matter whether you take the element like this or like this, there is not going to arise any kind of shear stress on any of these planes. All right. So what is the expression here? It's very easy to do it. You just pass a cutting plane. You just pass a cutting plane through the center in any direction, doesn't matter. Basically, you just take one hemisphere. Okay, just take one hemisphere. Just take a cutting plane in some direction like this and take one hemisphere. So we are going to end up with like this. All right, and the distribution of stress will be like this. And you understand that these blue arrows, they represent this sigma. So what is the equation? Tell me.
So sigma into 2 pi r into t equals p into pi r square.
Yeah. So it is exactly like this last case of the cylindrical pressure vessel. So this internal radius here is r, thickness again is t. I can just write it. This thickness is t, internal radius is r. So this is sigma into twice pi rt. That is equal to p times p times pi r square. So this sigma is going to be equal to PR by twice T. That's it. Okay, so you will encounter a number of problems in the context of pressure vessels where you will be just given the dimensions, the pressure, and you will just have to use this formula, either PR by T or PR by twice T for the cylindrical pressure vessel, and for spherical pressure vessel is even easier. You just have to use this PR by twice T to get the stresses. That's very, very easy. However, as I was telling earlier, especially in the context of the cylindrical pressure vessels, sometimes you are asked to do certain special things. For instance, suppose you are given a pressure vessel like this. So now we are talking about the actual problem situations. What is sometimes asked is that you know how to find out the stress, these stresses. But you may be asked to find out the stresses in an element which is oblique like this. So you will be asked to find out all these stresses. Okay, so in an oblique element, what is the motivation? Is it just because for fun people are asking those kinds of transformations? Actually, no. Okay, it is not just to give you some kind of an like a more difficult exercise that you have to do this extra step of transformation. It is not like that. There is an actual engineering motivation behind asking you to find out the stresses on this oblique element. You see, these cylindrical pressure vessels, they are actually fabricated or manufactured by welding together a long roll of steel or a long roll of aluminium in the form of a helix. Okay, what I mean by that is that they start with this very long roll of metal, and then they roll it up in the form of a helix. I cannot draw this properly, okay, so please don't mind. But when you do that, what happens is that you will see that these kinds of markings are present. These kinds of helical shaped markings are present on the pressure vessel. So this long strip of metal, when it is rolled and put in the form of a helix, they have to be held together, the edges of the helix, so they are welded here. So these yellow colored marks that you are seeing, they are the welded joints. Now along those welds, there is a higher chance of failure or the higher chance of the pressure vessel bursting open. So usually what is asked is that along this kind of a helical mark or helical weld, you are asked to find out the stresses which are perpendicular to the weld and parallel to the weld. And as you can see, what you are being asked here is basically just a transformation of this kind of a fundamental theory where you obtain the sigma 1 and sigma 2. From that information, you find out the stresses along this helix, perpendicular and parallel to this helical direction. Sometimes the question is twisted a little bit, and what is done is that some kind of strain rosette is attached near this helix. Okay, so some kind of strain rosette, as we have studied in the previous chapter, it is attached here. The values of the strains are measured, and based on that, you are asked to do some kind of design calculations. Okay, so based on the fundamental theory of pressure vessels, the sigma 1, sigma 2 things, as well as applications of the previous concepts, many different interesting things can be discussed. One very important thing which I have not discussed is that even though you know the total dimensions and the pressure and everything, there is another consideration which is to do with the change in the diameter of this cylindrical pressure vessel or the spherical pressure vessel, which I will cover in my next class. Okay, so thank you very much. You can go to your next class.
Excuse me, sir.
Yes.
So I have a doubt, sir. So can you go to upper slide?
Yes.
So I did not understand some more upper. So in that axial symmetry.
You mean the slide previous to this?
Yes, sir.
This one? Or previous to this? This one?
Yes, sir, this one. So actually, so you told that if del by del theta is equal to 0, then we can call it as axis symmetry.
So if it is axisymmetric, we can say that the del theta of anything is equal to 0.
So here anything means a pressure or stress like that?
Anything, displacement, stress, pressure, external loading, whatever.
So suppose if there is an so on left hand side you draw in one circle, means
Yes.
there is a like loading or pressure like
I'll draw once. Yeah, I'll draw one.
So will it not create that shear stress? And if we take a particular like element,
Yeah.
if we take a particular element, so it will not create a shear stress.
So you see this thing. So look at the epsilon r theta. Okay. So epsilon r theta, the sources of non-zero, what it can be. If del theta of this u had been non-zero, then epsilon r theta could have been non-zero. But we are saying that it is perfectly axisymmetric. So del theta of anything is equal to 0. So this term, there is no hope from it. This is gone. Next we have del v del r and v by r. Fine. There is no del theta present here. Now we come back to our drawing. Suppose we have, suppose this is like a shaft and there is some kind of a loading like this. Okay, this is almost like a torsion. Is it not? This is like a torsion. So here you will definitely have points which are present here. They move from here to here as this thing deforms, because you know how to calculate the phi, right? Phi is equal to TL by GJ. That kind of thing, yes. You know. Phi means what? The material points are actually twisting. They are actually moving in the theta direction. So there is definitely a non-zero V. So V is certainly not equal to 0. So there you actually have this non-zero V present, and from that you can have a possibility that epsilon r theta is turning out to be non-zero, which means that you can have, if epsilon r theta is non-zero, then sigma r theta is not equal to 0. But there is a little bit of a carefulness you have to remember. If the variation of the V with R is linear, then V by R and del V del R, they are going to be equal. In that case also, this is the subtraction here, no, then epsilon r theta may turn out to be 0. However, if the dependence of V on the R is non-linear, then these two things are not going to cancel out each other, then epsilon r theta will be non-zero. And then sigma r theta is also going to be non-zero. So there are certain delicate things involved. Yeah, tell me.
So sorry sir, but I did not understand what is U and V here, sir?
So U, yeah, U is the variation or is the displacement along the radial direction. Okay, so let me write this. U displacement in R direction, and V is the displacement in theta direction.
Okay, sir.
So if you have a material point here under the deformation, if this material point is going from here to here, that is captured by the U variable. And if this material point goes from here to here, that kind of displacement is taken care of by the V. So this is U, this is V.
Okay, sir, got it, sir. But sir, in twisting, actually we are assuming that V by R and del V by del R means their subtraction will be 0 because they are linear.
Yeah, if they are linear, then del V del R and V by R are going to be linear, equal.
Yeah. So, yeah. But suppose if in case it is not linear,
then you will definitely have epsilon r theta.
Okay, sir. Okay, sir. That was my thought. Thank you, sir.
In fact, in the torsion of non-circular shafts, for like this thing,
Like rectangular
shaft, yeah, square shaft or rectangular shaft, you will have shear stresses present very much.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you.